This unit of Algebra 2 introduces us to some completely new material. We will study permutations, factorials, and combinations. We will also learn to expand binomials by using a binomial theorem and Pascal's triangle. Finally, we will review how to use probabilities and odds. Let's get started with permutations. A permutation is the arrangement of a definite number of elements into a particular order. For example, let's arrange the elements of sets X and Y into ordered pairs. The definition of a permutation states that the elements must be arranged in a particular order. Therefore, we will choose the first member of the ordered pairs from set X and the second member from set Y. When A is used as the first member of the ordered pairs, R, S, and T can be used as the second members. This creates three different ordered pairs. Next, we use B as the first member of the ordered pairs. Once again, R, S, and T are used as the second members of the ordered pairs. This produces three more ordered pairs. Since there are no more elements in set X to use as the first member of the ordered pairs, the permutation is complete. The permutation of sets X and Y produces six distinct ordered pairs when the first member is chosen from X and the second member is chosen from Y. There is a special relationship between the number of elements in the sets and the number of resulting ordered pairs. Notice that there are 2 elements in set X and 3 elements in set Y. When we multiply the number of elements in set X times the number of elements in set Y, the product is 6. This is the number of distinct ordered pairs that can be produced from set X and set Y. Therefore, to determine the number of possible ordered pairs that can be derived from 2 sets, we simply count the number of elements in each set and then multiply the 2 numbers together. Let's find the number of possible ordered pairs that can be produced from set A and set B. The elements of set A make up the first member of each ordered pair, and the elements of set B compose the second. First, we count the number of elements in each set. There are 7 elements in set A and 5 elements in set B. Then we multiply 7 times 5, which equals 35. There are 35 different ordered pairs that can be produced from the permutation of set A and set B. Permutations can also be used to find the number of possible arrangements of numbers and letters other than in ordered pairs. Suppose we needed to know how many odd natural numbers have 4 digits. First, we must consider the sets needed. Set A consists of the 10 elements we use in our number system: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Set B is the set of odd numbers from set A: 1, 3, 5, 7, and 9. Since we are solving for the number of odd natural numbers with 4 digits, we can set up a diagram like this. Each blank represents one of the 4 digits of the number. Next, we need to determine how many elements can be used in each of the blanks. In the first blank, all of the elements of set A, except 0, can be used. If we used 0 in the first blank, the number would then become a three-digit number. The elements 1, 2, 3, 4, 5, 6, 7, 8, and 9 are the only values we can use in the first blank of the four-digit number. Therefore, there are 9 possible choices for the first blank. In the second and third blanks, all of the elements of set A can be used. Therefore, there are 10 choices for each of these blanks. Since we have stated that we are solving for the number of four-digit odd natural numbers, only the odd numbers can be used in the fourth blank. These are the elements of set B. Therefore, there are 5 possible choices for the fourth blank. Now that we have determined how many possible elements can be used for each digit, we simply multiply. 9 times 10 times 10 times 5 equals 4,500. You may use a calculator for these computations. Therefore, there are 4,500 odd natural numbers with 4 digits. Another method for solving this problem would be to write out all of the odd 4-digit numbers from 1,000 to 9,999. Then we would need to count all of them. The result would still be 4,500, but as you can imagine, that would take a long time. Using permutations is a much quicker method. Remember that a permutation is the arrangement of a definite number of elements into a particular order. To solve a permutation, first determine the number of elements in each member of the given arrangement. Then multiply those values. In Lesson 1, we were introduced to permutations. We used permutations to find the total number of distinct ordered pairs that could be derived from 2 sets. Now we are going to study a special notation used with permutations. It is called a factorial. Factorial notation is used to determine the number of distinct ways a group of objects can be arranged. This is the symbol used for factorial notation. The exclamation point is not a command to shout the letter N. Rather, it is a symbol used in algebra and is read N factorial. It denotes a series of multiplication using all of the integers from n to 1. For example, 5 factorial equals 5 times 4 times 3 times 2 times 1. When the factors are multiplied together, the product is 120. Therefore, 5 factorial equals 120. 7 factorial equals 7 times 6 times 5 times 4 times 3 times 2 times 1. When these factors are multiplied, the product is 5,040. Therefore, 7 factorial equals 5,040. Now that we know how to solve a factorial, let's study a couple of problems involving factorials. Here are 3 balls and 3 boxes. How many different ways can the 3 balls be arranged in the 3 boxes? If the red ball is placed in the first box, the blue ball can be placed in the second box, and the green ball in the third. This is one way the balls can be arranged. We can also place the green ball in the second box and the blue ball in the third box, while leaving the red ball in the first box. This is a second way to arrange the balls. Now we can place the blue ball in the first box, the red ball in the second box, and the green ball in the third box. This is a third way to arrange the balls. We could continue to rearrange the balls in the boxes until we have exhausted all the possibilities. But there is an easier way to find the number of ways the three balls can be arranged. We can use factorial notation. The number of different ways the three balls can be arranged in the three boxes can be found by simply solving 3 factorial. 3 factorial equals 3 times 2 times 1. The product of these factors is 6. Therefore, 3 balls can be arranged in 3 boxes 6 different ways. Factorials can also be used to determine the number of ways the letters of a word can be arranged. How many different ways do you think the letters in the word peanut can be arranged? Before we solve this problem, take a guess at how many ways you think it will be. There are 6 letters in the word peanut, so the solution is found by solving 6 factorial. 6 factorial equals 6 times 5 times 4 times 3 times 2 times 1. The product is 720. Therefore, the letters in the word peanut can be arranged 720 different ways. Did you guess that there would be so many different ways to arrange just 6 letters? We could have written out a list of all the different ways to arrange the letters, but don't you agree that it would have taken quite a bit of time to do so? Factorials make these type of problems very simple to solve. Let's consider another special kind of permutation. These permutations will involve arranging a set of elements taking only a certain number at a time. For instance, how many ways can 7 different books be arranged using only 4 at a time? Since all 7 books are not being used each time, we cannot use the factorial notation we learned in the previous lesson. Instead, we use a special formula. In this formula, P stands for permutation, N represents the number of different elements, and R represents the number of elements to be taken at a time. The result is a series of multiplication similar to a factorial, except that the last factor is not always 1. To find the number of ways 7 books can be arranged using only 4 books at a time, we use the permutation formula. In this problem, N equals 7, which is the total number of books. R equals 4, because we are using 4 books in each arrangement. Let's substitute these values into the formula. Next, we do the necessary subtraction within the parentheses and brackets. Study this procedure carefully. 7 minus 1 is 6. 7 minus 2 is 5. Next, we see that 4 minus 1 is 3. And then 3 subtracted from 7 is 4. Therefore, we have a series of multiplication in which 7 is the first factor and 4 is the last factor. All of the integers between 7 and 4 comprise the other factors. When the multiplication is performed, the product is 840. Therefore, we can arrange 7 books using 4 at a time, 840 different ways. Problems which require the permutation formula are solved much the same way as factorials. The first factor of the series is always the total number of given elements. However, the last factor is not always 1. In fact, the last factor will usually be different for each problem. Therefore, the easiest way to solve problems which use the permutation formula is to solve for the last factor first. Let's find how many ways the elements in set X can be arranged taking 5 at a time. Consider the permutation formula again. The value of n is 8 for this problem because there are 8 elements in set X. The value of r is 5 because we are to use 5 elements in each arrangement. We know that the first factor of the multiplication series is 8 because the value of n is 8. Rather than solving for each of the other factors, let's just solve for the last factor. The last factor is n minus r minus 1. For this problem, we already established that n equals 8 and r equals 5. When we substitute these values into the formula for the last factor, we find it to be 4. We already know that the first factor is 8, and now we have solved for the last factor, 4. All of the integers between 8 and 4 make up the other factors. Therefore, the multiplication series is 8 times 7 times 6 times 5 times 4. The product of these factors is 6,720. Therefore, the elements of set X can be arranged 6,720 different ways when taking 5 elements at a time. If we solve for the last factor first, we do not have to memorize the entire formula. We know that the total number of elements given is the first factor. We solve for the last factor using the formula. Then we know that all of the integers between the first and last factor make up the other factors of the series. Before we move on to the activities, let's solve one more problem. This problem will create a factorial like the ones we solved in the previous lesson. How many ways can the letters in the word light be arranged? Since the problem does not tell us to use a certain number of letters in each arrangement, we will use all 5 letters each time. For this problem, both n and r equal 5. This is because there are 5 letters in the word light, and all 5 letters will be used in each arrangement. We know that the first factor of the multiplication series is 5 because n equals 5. Now we want to solve for the last factor of the series using the formula. When we substitute the values of n and r into the formula, we can solve for the last factor. 5 minus 1 is 4. Then 4 is subtracted from 5, which is a difference of 1. Therefore, the last factor of the multiplication series is 1. Therefore, the permutation is 5 times 4 times 3 times 2 times 1. This is the same as 5 factorial. Whenever the values of r and n are the same, the permutation is n factorial. The product of this multiplication series is 120. Therefore, the letters in the word light can be arranged 120 different ways. Finding the number of ways to arrange a set of elements when using only a certain number of them each time is not difficult. Remember that the first factor of the multiplication series will always be the total number of elements given. The last factor in the series is derived from the formula. This is the